Sorry, just remind me to record the class from tomorrow, all right? I just forget it. Scalar multiplication, okay. Then we have vector addition, right? uh, One more important concept I think we need to cover is what, dot product. There is one more concept called cross product. However, it is not at all used. Very less used. Okay. Yes. Someone is trying to say something. No. Okay. Then we need to discuss about matrix multiplication, and yeah, one more understanding that is required is the transpose. Right. Prajna, please mute your mic. I can't hear your voice as well. If you are trying to ask something, ನಾನೇ ಮಾಡ್ಲಾ? ನಾನೇ ಇಲ್ಲಿಂದ ಮಾಡ್ಲಾ? Oh, she left the meeting itself. Why do you guys panic so much? Okay, so as far as the linear algebra part is concerned, we are taking one or multiple uh, data representations and do some operations on them. Okay, these operations are essentially for some kind of transformation of data. Okay, the linear algebra just working on a scalar doesn't mean anything. So the basic structure that we will have to take care of or look at is the vector. Okay, if I have a vector, say something like a is equal to, let us say for example, it is, I will take a 2D vector so that it makes sense to explain, right? 3 comma 4, this is the vector that we have, right? Let me first give you a graphical understanding how it could look like in a basic sense, right? So if I take this in physics, if you have studied, or in mathematics if you have studied, this looks something like, this could look like this, right? The x cap plus 4y. Now what is this? If we draw it like the draw it on the Cartesian plane, this is x, this is y, then 1 2 3 x's, and then 1 2 3 4 y's. So this essentially is the vector, right? This is the x component and this is the y component. This is what the understanding is, right? Now say for example I multiply this with this thing with 0.5, right? What is going to happen now? 3 multiplied with what? 0.5 becomes 1.5x cap, plus 4 multiplied with 0.5 is going to become 2y cap, right? Then how does the vector look like? 1.5 cap, 1.5 in the x side, right? And then 2y cap means 1 2, right? 2 is here, 1.5 is here. Going to be the resultant. Can you see this? No. Why doesn't anyone tell me whether it is coming through or not on the screen? Yeah, not coming. Exactly. Now you got it right. See, I told you in the beginning itself, you, why don't you just unmute yourself and tell me, sir, screen is not coming? Why? Anyway, fine. Right? This is what I was explaining. If the vector is like this, when I multiply this with 0.5, right, the resultant vector is going to look like this, correct? And then if we draw the same vector, then the resultant vector, then it is going to be something like this here, correct? What's happening here? If I multiply with, say for example, 2 instead of 0.5, right, what happens? The 3x cap plus 4y cap is going to become 6x cap plus 8y cap, correct? And then this is going to be like this, somewhere around here, and from 4 it is going to raise up to this point, right? Some higher point. The vector is going to look something like this. Is it correct? Can you make sense of it? Right. What is happening essentially here? When we multiply a vector, right, with a scalar, then it is going to be a scaled a vector. That is what we call it. What does that mean? The a vector is going to get scaled. Okay, either elongation or shortening. Is it clear? Can you understand this? Okay, fine. Pretty simple. There is nothing to be feel complicated, right? Just any vector. For example, if I take an image like yesterday, right? 0 0 0 0 0 0 and then 0 0. If I put in say for example 127 some odd value, right? If this is the image, how is the image going to look like? This will be something like this, right? Let me take this one. Don't mind the color, I'm just trying to tell you that it is going to look something like this, right? Right, not fully black, some gray color. However, when I multiply this matrix with 2, let's say, then what happens? The black colors, sorry, it is the inverse, right? These are the black colors and this is going to be gray. Now when you multiply this with 2, what happens? The black colors are kept as it is, but this 127 is going to get doubled, right? Then how does it look like? If I draw it once again, it will be exactly like this. This part is going to look black, but the center part is going to be white completely. However, in this example, what is it going to look like? Let me erase this because it is wrong, right? So it is going to be something like this. This entire part is black. There is no problem in that. The center part is going to be gray. Make sense? So scalar multiplication, what does it do? It simply scales it, either intensify or de-intensify, either elongate or shorten it. The important factor here is when you multiply a vector with a scalar, right? It doesn't affect its direction. The direction, if you look at this, the direction is kept as it is. Just the length is changing, isn't it? So the direction is kept as it is. Make sense? Shall we move on to the next one? Okay, fine. So the next operation that we were talking about is what? The scalar, sorry, scalar is done. So what was it? Vector addition, right? If I have two vectors, I will again take the physics example because it makes sense, right? So if I have two vectors, say for example, one pointing in this direction and another pointing in this direction, right? Vector A and vector B, right? If you want to imagine this, just think about it in this way. I have an object over here, some box is sitting there, okay? Or let me take a more intuitive drawing. If I have a box like this, right? What I do is I come from this direction and kick the box in this manner, in this direction, right? One force is being applied here, and another person, a friend of mine, he comes from this direction and kicks the box in this direction. Then how the box is going to move? Something like this, right? So exactly what is happening? This force being applied here is a vector. This force being applied here is a vector, and this is the resulting vector. What's happening? Both these vectors are getting added, and this is the result. Okay, so exactly the same way, if I have to represent it in a graph, right, it is going to be something like this. If I have a vector over here, then another vector in this direction, the addition of these two is going to be somewhere in this direction. Okay, this is A vector, let's assume this is B vector, and this is A plus B vector. Okay, generally these operations, if I take some A vector as 2 comma 3, right, and then I want to offset this or put a bias to this particular vector, is what we say. If I, let's just assume we want to shift it somewhere based on a requirement, then we do the vector addition. The vector B will be a standard some standard vector that we take, and then we add that particular thing. For example, I have a picture. Let's okay, take this example. I have a picture, okay, which has a light white overlay, something like a photo taken facing the sun, and the picture contains a white overlay. Do you want me to show an image or something, or can you visualize, right? Then if I subtract that particular picture, addition and subtraction are almost similar, right, with a negative sign. So if I subtract that picture with another picture that contains only the white noise, then what is going to happen? That particular white noise is removed and whatever is left out is the actual image, right? Makes sense? That is one of the examples for use of vector addition and subtraction. Make sense? If you are finding it difficult to understand, don't worry, we can actually go through it later. But is it clear or not? Some concepts are difficult to explain in this manner, no? And with people like you who do not respond, it's even harder. Come on, please just tell me intuitively what this addition, this part is understood or not. We'll also see mathematically how it works. Okay. So generally, one person said understood, good enough for me, right? If I have a vector something like this, 2, 3, and then I have another vector, say b vector, that is, let's assume 2 comma 2, then how do you add these two? A vector plus b vector is going to be what? 2 plus 2, 4. The individual elements are added together, right? 2 plus 2, 4, and 3 plus 2, 5. This is going to be the result. Now, do you want me to draw this? Let us see whether this checks out or not, right? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 6. Right? What is a vector? 2, 3. So 2 and 3. So this is one vector, right? A, and B, 2 comma 2. 2 and 2. This is B vector, right? What is the result? 4 comma 5. 1, 2, 3, 4. Then 5. 1, 2, sorry, 1, 2, 3, 4, 5. Right? I should have taken a better thing, right? Make sense? All right. So let's move on. This is not even that great information to know because most of you already know this, right? Just understand, when we are adding two columns or two vectors, we are essentially calculating the sum of two vectors. Don't worry, nothing else. It is even very less used. Nothing uh, interesting is there. The next concepts that we are going to cover is going to be something important. What was it? I had written it here, right? Dot product. This for these things, right? It is a fuse of the old mathematical concepts ported into the data science field. That is why I'm taking the mathematical way of explaining things so that you can understand the concept and then port it into the data that we are going to use. Make some sense in that manner. No? The dot product. Can anyone explain what is a dot product? Somebody please unmute yourself and explain the dot product. Whatever you know is good enough. Shall I pick names? So there is Isfa Taranum.
It multiplies two vectors and give a single number.
It multiplies two vectors and gives a single number. Mhm. Anyone else has another answer? Can I ask, say, Sharath? Sharath? Sharath, Padigir. Sum of the product. Multiply two vectors and sum becomes third vector. Srishti Naik. Srishti Naik. No? Okay. So a dot product essentially tells you the similarity between two vectors. Okay, how do you measure it in real time? The intuitive idea that people give is, say for example, I have two vectors like this, right? A is in this direction, B is something like this. If I flash a light or put a light in this point, right? Then the shadow that this B vector is going to cast on A, right? This part, this is the dot product. So what is this essentially telling you? It is telling you the effect of B on A or in A, or the presence of B in A. Okay. If these two vectors are in the same direction, right, then the shadow that it casts is going to be lengthy, right? If the direction is something like this, then the shadow is lengthier. However, if the direction is, let us say this is one vector and another is like this, right, then the shadow that it casts will be what? Very small, right? Then we say that this these two vectors, A vector and B vector, are very apart from each other, or they are not at all similar to each other. Make sense? This is something that you need to understand, because the dot product is what gives away the concept that I had shared in the initial draft, right? The pre-reading material. How do you find out the similarity between two people? Are they going to watch similar movies or what? Those things, right? This is what it is, the dot product. How do you calculate it? Mathematically, it is given as a vector dot b vector is given as the magnitude of a vector multiplied with magnitude of b vector multiplied with cos theta, where theta is the angle between the two. Okay, right? This is the mathematical formula. However, we will not use this in data science. When you have a vector something like 2 comma 3 and b vector is equal to 4 comma 5, then a dot b is going to be what? 2 multiplied with 4, right, plus 3 multiplied with 5. This is the value that it is going to be. That is nothing but what? 4 into 2, 8 plus 15 is equal to how much? 23, right? Now, if you look at this particular mathematical expression, this point also makes sense, right? If the angle between the two is very less, I hope you know cos theta is going to be, when theta becomes almost zero. Say for example, I have two vectors like this. This is A, this is B. If this is the case, the angle is essentially zero, right? Cos zero is what? Cos zero becomes 1, and this is what it gives you. A vector, magnitude of A vector multiplied with magnitude of B vector. Okay. However, if the vectors are like this, perpendicular to each other, that is 90 degree to each other, then this angle is going to be what? 90 degree. Theta cos 90 is what? 0, right? The dot product is going to be 0. This is very important. When you have a dot product 0 between two vectors, that means the two vectors are not at all close to each other, right? So essentially, what is a vector? As per the understanding that we developed in the last class, it is a profile, right? A vector is nothing but a profile, right? Then if I say dot product between two vectors is 0, means what? The two profiles do not have any similarity. Okay. When I say the dot product is very large, then what does it tell you? It tells you what? The two profiles are exactly similar or very, very similar. Make sense? Because the shadow that this casts on A is going to increase, means what? There is more of B inside A, right? When theta becomes close to 0, means what? Both vectors are almost coinciding with each other. Both the directions are same, right? That is why we say they are similar. And this concept of dot product being 0 or very high comes in something called feature analysis. Okay, and for linear regression model that we are going to build, that is very important. If there are two columns, we treat each column as a vector in that case, and if they are similar to each other, they are following some tradition, a trend, then we will have to ignore one of them and use only one out of the two. We will discuss that later. Okay, but dot product is very important. Fine, don't worry. We will not, I think we don't get enough time to execute today. We will do the execution tomorrow. I will complete with the theoretical concept. Okay, dot product is done. Cross product is not at all important for us. uh, it follows the right hand thumb rule and everything. Let us say, just for your understanding, it is defined only for 3D, right? Then if I have two vectors, say for example like this, the cross product or the vector multiplication is going to be in the other direction. If you want to visualize this, if the two vectors are uh, in the plane of this particular screen, the third vector is essentially either pointing uh, into the screen or away from the screen, perpendicular to the screen. Can you make some sense of it? Is it possible to visualize? This is how we can describe this. Okay, but not very much used, so don't worry. All right, what is that? Matrix multiplication. Hmm. I think we will have to spend 3 hours for this. Okay, what is matrix multiplication? Essentially, uh, the dot product in batch mode, right? In parallel mode, we can say. Let me give you one small example for that. If I have, say, for example, three students, or let me tell you I think you already know how to do matrix multiplication, right? So let's focus on the use case here. Let us say students were evaluated for a placement test on three criteria. Let's assume one is based on aptitude, and then another criteria was, let's say, communication, and the last criteria was the coding, let's assume. Okay, all were 100 marks tests. So let's say student 1, so this essentially becomes our table, right? So student 1 got, say, aptitude, he got 90 marks. For communication he got, say, 30 marks. Then for coding maybe he got some 60 marks. Okay, and then another students 2, he got 75 marks in aptitude, 78 in communication, and maybe 80 in coding. He is an average person, let's say. Another person is good in it, aptitude, fine. Communication is also very nice, let's say 90, but his coding skills are, let's assume, to be very, very weak. Let's put it as 20, right? Now, there are two companies, let us say there are two companies coming in. One is a sales based company, right, which requires which skills? Communication mainly, right? And also aptitude matters, but coding is not needed for them, right? And there is another tech company, let's say, which requires what? Communication is not that important for them, aptitude is necessary, and then coding is also necessary. Coding is of high weightage for them. So if you want to calculate which student, this is a vector, right? For every student we have a vector. So which student could be placed in which company, if you want to look at that, then what we essentially do most of the times is, for this sales company we create a vector, a weight vector based on their preferences. Here what happens is, every row corresponds to one of the qualities: aptitude, communication, and coding. Okay, so a sales company requires, say, for example, zero point 0.4 weightage out of 1. It is putting its percentages. So 0 0.4 weightage for the aptitude, and then 0 0.6 weightage for the communication. It doesn't require coding. Okay, and the tech company, this also has another criteria. Based on that, they require what? Aptitude is necessary for them, so let's say again 0 0.4, and then communication is not that required for them, let's put it as 0.1. Coding is extremely important, so let's put it as 0.5. Okay, the sum of them is going to be 10, sorry, 1, totaling up to 1. Now the basic idea is to use the dot product. If I want to calculate whether this student 1 gets placed in here, is more aligned to get placed here or here, is to do what? This is 1, 90, 30, 60 is one vector, and then dot product with what? 0 0.4, 0 0.6, 0. This is one, and another operation 90, 30, 60, dot product with what? 0 0.4, 0 0.1, then 0.5, right? This gives you what? The similarities, whether these scores match with this requirement, whether this score matches with this requirement, correct? So wherever you get the highest score, that there is a high probability that that student will get placed in that particular company. Making sense? This is the dot product, application of dot product, how it is going to work. Make sense? Okay, so now the same dot product calculation, I can write it like this. If I take the table as a what? A matrix, 90, 30, 60, right? The second student 75, 78, 80, then 80, 90. This is going to be one matrix. Each row corresponds to one single particular student, and each column, the first column corresponds to what? Aptitude, second one to communication, and the third one for coding, right? And these attributes have to be matched with the criteria that the company has set up. So that is for the first company, sales company, I will put it 0 0.4, 0 0.6, 0. For the second company, I will make it the second column 0 0.4, 0 0.1, 0 0.1. Intuitive understanding. We know that for a matrix, for two matrices to be multiplied, you will have something like this, right? M cross P can be multiplied with P cross N. These inner dimensions must match, right? This is the basic understanding for any matrix multiplication. But what does this essentially asking for? It is asking for the number of features, right, should match with the filters, the weightages. Here, this corresponds to what? Aptitude, and this each row corresponds to aptitude of company A, company B. Okay, so the aptitude marks from here is multiplied with the aptitude weightage of company A, and then communication marks from here get multiplied with communication weightage from company A, and then the coding marks from here get multiplied with coding weightage from company A. That will give you, and then when summed together, it will give you a particular value, and that value, if it is very high, then what? That student is going to, there is a highly likely that that student is going to get hired in that particular company. If that is going to be very low, that means the profile of the student is not in line with the profile that the company is looking for. Does it make any sense? Right. So what is happening here? The basic calculation is dot product like this, but when you multiply, when you use the matrix multiplication, we can actually batch process the data. So now with this one calculation, what are we doing? We are calculating the values for three students and two companies at the same time, right? This is what essentially matrix multiplication is for, right? Sometimes we also use the matrix multiplication for transforming the actual data. For example, if you have an image, you want to rotate the image, then some rotation matrix is used. When you multiply it with this particular matrix, that rotation matrix in that dimension, the image that is pointing, say for example, if this is the image, when you multiply it with that rotation matrix, it could point, it could become something like this. All kinds of transformations are carried out using matrix multiplications, right? So in deep learning models, this is the original matrix multiplication. However, there is one more, that is what? Element by element matrix multiplication, right? Why do we need that? Say for example, I have the same, for the same matrix, let us say I don't want this particular column at all. I'm not looking for coding at all. Then what can I do? The same matrix I use, I multiply it with what? Another matrix where I put in 1 1 1 1 1 1 and then 0 0 0. You multiply it element by element with this particular matrix, you will get what? Only this much. So basically in deep learning and AI models, these are called gating matrices. That means what to let go and what to keep, what to move past and what not to, what to block, right? So these gating filters or matrices basically use element by element multiplications. However, for other kinds of manipulations, we use this one, the original matrix multiplication thing. Is it clear? Okay. One last thing is the transpose. So the same table, if I take, right, aptitude, communication, coding, aptitude, communication, and coding, and this is student 1, 2, and 3, right? So if you look at this, what are we doing here? these things become the features, right? These are the features, and these are what? The vectors that we say, right? So this becomes the profile of one individual student. So every vector is representing one student here, right? What if I want to find out some analytics or some information about the aptitude tests, right? How all my students are performing in aptitude. If I want to find out that, then the central focus has to change from these students to the feature aptitude, right? In the same way, how each test is being carried out, or how students are performing in each test, if I want to find out, then what? Then aptitude should become one vector, communication should become another vector, coding should become another, and each student should become, sorry, one, two, three, one feature, right? Now, what is happening here? This is one profile, aptitude profile of my students, right? In that particular profile, these are the features, multiple students. How do you do this? If you want to change the perspective of the data for some analytics, then you do this operation. And how do you do this? It is essentially exchanging the rows with columns. If I have 1, 2, 3, 4, 5, 6, right? The transpose of this operation will become what? 1, 4, 2, 5, and 3, 6. If you look at this, each feature has turned into a row, right? Each profile previously has turned into one, a feature. Make sense? What is transpose? Yes or no? Okay. So I will stop here for the as far as the concepts are concerned, right? If you have any doubts, you'll have to ask me now. Please don't keep quiet, because it's not going to take you anywhere. Implementation part we will do in the next class. Yes, my laptop has stopped working suddenly, and I had to find a workaround for all these. Uh, I don't know how things were going. No doubts? Okay, Deepak Deshpandari said no. Were you able to understand what I said today? I actually skipped the extreme basics part, how you do the matrix multiplication and everything, right? Because I assumed you already know that. My focus was to give you a different perspective, how those operations are relating to the problems that we are going to discuss, the AI and ML algorithms, those things. So please, if you want some clarification regarding anything, just tell me. I'll wait for few more minutes. Nothing? Nothing? Okay then. Shall I end the session then? Okay. Thank you. Tomorrow we are going to do the implementation part of it. And if I find that something important is pending, like if I feel like you need to know something else as well, linear algebra, then I'll cover that part too. Tomorrow is going to be more practical and less theory. Okay. Thank you. I know today was more theoretically heavy, and I have been talking too much. The only thing I am feeling bad about is that you guys are not responding. Let's do one thing from tomorrow's class, right? When I ask a question, I will pinpoint somebody, whether you know the answer or not. You will have to unmute yourself and tell me something like, "Sir, I don't know the answer," or whatever you have to tell, something like that, right? That we should do. If you guys don't do that, maybe you will miss out on something that is there, and then yeah, not good at all. All right. Thank you. See you tomorrow.